Hey, what's up, chemistry people? Mr. Boylan here. As we take a look at our content objective for the day, we're going to look at how chemical equilibrium can be used to describe the proton transfer reactions of acid-base chemistry. Specifically, as we break that down for today, we're going to describe what's called the self-ionization of water and define the ionization constant of water, also known as Kw. We're going to find pH and pOH and calculate either pH or pOH for a given solution. This part will probably be what you are most familiar with when we start talking about acids and bases. And then lastly, we're going to use correct significant figures when working with logarithms, which is going to be a big part of those pH and pOH calculations. Okay, so first things first, as we try to understand the concept of pH and what that means, really, we need to understand what's going on with what's called the self-ionization of water. And although pure water is mostly molecules of water, conductivity measurements indicate that there are a small amount of ions in pure water, and that's due to what's called the self-ionization or auto-ionization of a small amount of the water molecules. Okay, now as you take a look at your notes, you're given an equation that represents that self-ionization or auto-ionization of water, and I'm showing you here a quick animation on your screen that describes what is happening there. Now, it's important to recognize that in this process, equal amounts of hydrogen and hydroxide ions are produced, each at a concentration of 1 × 10⁻⁷ molar. So we're talking extremely small concentrations of these things at equilibrium, which means that not a whole lot of water molecules will do this. Only 1 in every few billion water molecules will actually undergo self-ionization. But because these ions are in equal concentrations, we say that pure water is neutral. The equilibrium constant for this expression is known as what's called the ionization constant of water, Kw. So again, I know we're throwing a lot of K values at you in this unit. Recognize though that each K value simply is describing an equilibrium constant. The little subscript is just being a little more specific about the type of expression that we're describing. The Kw expression is going to be indicated here by the hydronium ion concentration times the hydroxide ion concentration. As you look at this, recognize that it's just the products in this expression. We don't have it over the reactants. And as you think about why, you want to think about what this expression has in the reactant side. It is 2 liquid water molecules. And remember, we only are going to include aqueous or gaseous species in our equilibrium constant expression. So we only have the products here for Kw. Each of those concentrations are going to be the same for the hydronium and hydroxide ion, and those will each be 1 × 10⁻⁷ at 25 degrees Celsius. Therefore, the Kw value at 25 degrees Celsius is going to be 1 × 10⁻⁴, or just the product of those two values. It is important to recognize that this reaction is an endothermic reaction. In other words, our heat will be a reactant. And just like other reactions, then Kw, the value for Kw will be affected by temperature. As you heat this up, as you add more heat, you will shift this equilibrium to the right, forming greater concentrations of hydronium and hydroxide. So as you look at this table for Kw, as you increase your temperatures, you get past 25 degrees Celsius, notice that your K value is increasing because you have greater and greater concentrations of these ions. However, recognize that you're producing equal concentrations of each of these ions. And so at higher temperatures, your neutral pH is not going to be exactly 7. It's also important to recognize, though, that Kw is a constant. So at a given temperature, at 25 degrees Celsius, which is when you will most commonly see it, as the concentration of one of those ions increases, the other must decrease in order to keep that value constant. So as we think about adding acid to water, we're going to increase the hydrogen ion or hydronium ion concentration, which will shift the equilibrium to the left and will use up some of that hydroxide ion. And so that hydroxide ion will decrease to maintain that constant value of 1 × 10⁻⁴. Now I put a couple of example values in here to illustrate that. Recognize that we're working with negative exponents. So a 1 × 10⁻⁴ is an increase in concentration from that original 10⁻⁷. Therefore, our hydroxide ion concentration will decrease to 1 × 10⁻�13. Likewise, when we're working with a basic solution, similarly, we're going to keep this value constant at a given temperature. So if we are adding a base to water, we're going to increase our concentration of hydroxide ions, again, shifting the equilibrium to the left, which means we will use up some of those hydronium ions to reform the water molecules in order to keep that equilibrium constant a constant. And then lastly, there are just some important relationships to walk away with as you think about the Kw expression. You are going to have an acidic solution if you have a larger number or a larger concentration of hydronium ions than hydroxide ions in solution. If those two concentrations are equal, then you will have what is called a neutral solution. And if you've got a greater concentration of hydroxide ions in solution than hydronium ions, you will have a basic solution. Okay, and that ultimately brings us to the idea of the pH scale, which for most of us we've heard of before we've gotten to this point. And it's typically what we think of when we think of something as an acid or a base. But as we think about and try to understand what the pH scale is, or what is it a measure of, when we say something has a pH of 2 or a pH of 10, what does that mean? Basically, we're looking at expressing, what are the concentrations of the hydronium ions or the concentrations of the hydroxide ions in that solution. And it can be really very cumbersome to deal with because we're often talking about concentrations that are very small. And so, as you'll learn, the pH scale incorporates logarithms to make those values easier to work with. And so just as a quick refresher, if you think about an example of a logarithm, log, which is just the shorthand version of logarithm, log base 2 of 8 is equal to what? In this case, it's equal to 3. And if you're wondering or have forgotten, essentially remember 2 to the third power is 8. Now, in this class, we're going to be working with the common logs, or log base 10. And we'll also be working with much smaller or much larger numbers than these that you see in this first example. But I always like to go back to an example that I'm really familiar with, or one that's easy for me to work with. So it helps me understand when I work with those numbers that are much larger and much smaller. So as you look at this example, log base 10 of 1,000,000 is equal to what? Again, we're trying to think about what power should I raise 10 to get 1,000,000. In this case, we need to raise it to the power of 6. So 10 to the 6th power is 1,000,000. Okay, now as we think about the pH scale, a more common logarithmic calculation that you'd have to do is something like this. Negative log base 10 of 1 times 10 to the negative 7. What power do we have to raise 10 to get this number 1 times 10 to the negative 7? The answer here is 7. Now, bear with me. 10 to the negative 7 will give me 1 times 10 to the negative 7. Recognize that when we're talking pH, we're talking about the negative of the common log. So if we were just doing log base 10 of 1 times 10 to the negative 7, it would be negative 7. But because we're taking the negative log, we're going to end up with a positive value of 7 there. I'm going to do this same calculation using standard notation. So negative log base 10 of 0.0000001 is equal to what value? In other words, what number do I have to raise 10 to get this number? And that, again, is going to be 7. Again, recognize 10 to the negative 7 is 0.0000001. Again, recognize we're taking the negative log, so it's not going to be the negative, but the positive value. And ultimately, when we say pH, we mean take the negative log of the hydrogen ion concentration. And so the long and the short of it here is it's a lot easier for chemists to say, oh, the solution has a pH of 7. It's a lot easier to deal with than to say, oh, the hydrogen ion concentration of this solution is 1 times 10 to the negative 7. Simply by saying, oh, the pH is 7, you need to recognize that that means that the hydrogen ion concentration is 1 times 10 to the negative 7. Whew. And so as you look at your pH scale here, recognize that if you were to take the negative logs of each of these hydrogen ion concentrations, you would get these respective values. Again, much easier to say, oh, this solution has a pH of 1 instead of saying, oh, this solution has a hydrogen ion concentration of 10 to the negative 1. Or this solution has a pH of 10. Much easier than saying, oh, this solution has a hydrogen ion concentration of 1 times 10 to the negative 10. So just an easier way to describe what is going on in the solution. What you may be less familiar with is the pOH scale. It's very much the same as the pH scale, except instead of looking at the hydrogen ion concentration, we're looking at the hydroxide ion concentration. Works the exact same way. Recognize that if you take the negative log of the hydroxide ion concentration, you'll get these pOH values, much like you did with the pH scale. And then really importantly, you need to understand the relationship between the pH and the pOH scales. And we can derive that to be what you see on your screen there, where pH plus pOH equals 14. Now, I really like this graphic here. So if you're to look at this graphic and say, oh, the pH of a solution is 4, that means the pOH of that same solution is 10. So if a solution has a pH of 4, we recognize that to be acidic. If we have a pOH of 10, recognize that's also acidic solution. So we'll practice that and we'll work with that a little bit, but you're given a quick diagram there that sort of sums up the relationships between hydrogen ion concentrations, hydroxide ion concentrations, what pH is and what pOH is for neutral, acidic, and basic solutions. Okay, and then lastly, we need to talk briefly about the understanding that using the letter P in front of anything means to take the negative logarithm of that thing. Another common P scale is the pKa scale, where you just take the negative log of your Ka values. And again, it just makes those really small numbers that we see a lot easier to work with. Okay, and then the last thing to think about when we're talking about pH calculations is you've got to watch out for significant figures when it comes to logarithms. There are as many digits after the decimal point as there are significant figures in the original number. So when you are working with pH calculations, if you're given a hydrogen ion concentration of 1.0 times 10 to the negative 3, this translates to a pH value of 3.00. So recognize however many total digits are in your concentration, that's how many digits come after the decimal place in your pH value. So be on the lookout for that as you work through pH calculations.